before I focus more on linear time invariant systems, let us look at some of the signals. Okay, these are very basic signals, though I may be discussing them as example, but they are very vital from the analysis of LTI system point of view. Okay, one of the signal that is of interest to me is delta function delta n. This is defined to be 1 when n equal to 0 and 0 otherwise. If I want to plot this signal, it will look like this. This is my time axis, which is the running index n. This is n equal to 0, n equal to 1, 2, 3, minus 1, minus 2 and so on. At 0 it has value 1 and it is 0 otherwise. This is delta function. Suppose I say the following thing, instead of delta n, I consider a signal delta n minus n0. Clearly delta n minus n0, if I use this definition, it will be 1 if and only if the index, which is n minus n0 here, is 0. That is, when n minus n0 is 0, that is n is equal to n0. So this is going to be 1 if n is equal to n0 and 0 otherwise. And this is how it can be plotted. This is the 0 point and this is the point n0. So at n0 I have value 1 and 0 otherwise. Please see this n0, I have taken this to be positive, but it is not necessary. That if n0 is negative, then this 1 is going to appear at here, because n plus n0 should be equal to 0 for this to be 1. That means n should be equal to minus n0. So it is on the negative time scale, it will be appearing somewhere here. So this we can regard as the delayed version of the delta function. This is one class of signal that is of interest to us. Let us see what is the utility of this particular signal in the context of analysis of linear and time invariant system. Let us pick up any arbitrary signal x of n. X of n is any arbitrary discrete time signal. Okay, how do I plot this signal? Suppose at n equal to 0, its value is something, let me call that value x of 0. At n equal to 1, it has some other value, let us call it x of 1. Then I say x of 2. At 3, this is 1, this is 2. At 3, it has some other value, so x of 3, and so on, as a function of n. This is how I can plot any arbitrary discrete time signal x of n as a function of n. It is very easy to break it into so many different signals. Say for instance, I can write this as one signal which is appearing only at n equal to 0 with height 0 and 0 otherwise. Then I can also write another signal which is x of 1 at 1 and 0 otherwise, and so on. At particular instance, suppose this at instant k, it will be x of k. So I can have a signal, a value sitting at k, at instant k the value is x of k, some pulse sitting there of that strength. Okay, so if I add all these signals, I am going to get this signal. If I add this signal plus this signal plus this signal, okay, all these signals, I am going to get this signal back. Is it clear? Let us try to see in terms of signals what is this. I have defined delta n, and with that definition of delta n, this signal can be written as nothing but x0 delta n, because when n is equal to 0, this is 1 and the strength is x of 0, at other instant delta n is 0, so nothing appears at any other point. Similarly here, this signal is a function sitting only at 1 and is 0 otherwise. So I should be able to write this in terms of delta function as x1 multiplied by delta n minus 1. So only when n is equal to 1, this will have a non-zero value equal to x of 1 and 0 otherwise. So these, and let us say this signal xk sitting at k in terms of delta function can be written as xk delta n minus k. So I can write my signal x of n as sum of all these signals, right? So let us write down, I have written this graphically, let us try to write down mathematically. And this is a important step. This representation of x of n in terms of only delta function is an important step in the direction of characterization of LTI system. One of the characterization or time domain characterization of LTI system. In particular, right now I am only discussing the discrete time LTI systems. So I can say that any x of n can be written as weighted sum of delta functions. Delta n minus k is an impulse which is sitting at k and with height xk, and I sum up all these signals as k ranges from minus infinity to infinity. Basically I would have generated x of n, right? Let me, instead of writing this n, I will just write x for my convenience, because it confuses. If I say x of n, then I am considering the value of map x at an instant n, but I want to regard them as map as a whole, and I am considering x to be a map. So this delta is also a map. So I, instead of writing this, either I write delta delayed by k, or more appropriately in the notations that I had considered earlier, I can write it as follows: x equal to summation x of k dot delta. Okay, k dot delta means delta delayed by an amount k. So xk is the height, and this is now a map, delta map, delayed delta map. So the map x can be written as sum of all these maps, right? And now when I pass this x through a system which is a linear system and which is also a time invariant system, then the following thing happens: x goes to Rx, pass through a system. R I am denoting as response of an LTI system. Okay, any LTI system, I am denoting that as R. So x goes to Rx. That means this is the picture. I am replacing for x its equivalent representation in terms of delta function. Now R is linear. Let me assume the following, that it is bounded linear and R can be pushed inside. So I can write this as summation xk response of k dot delta. That is, you add the response of all those components and add them. I had broken x in terms of so many signals. Linearity basically is trying to say that you consider response of each one of them and add them up. That will give you a response of total x. But then we had also made an assumption that our system is not only linear, but our system is also a time invariant system. So time invariance also starts playing its role here at this juncture. Suppose I denote h to be response of the system to delta. Okay, h is also a map. So if I want to evaluate that map at instant n, basically I am evaluating R delta at n, and h of n in the literature is called impulse response of the system. H of n because it is response of the system to an impulse function. Delta n is also called an impulse function. Okay, so this is the impulse response of the system. Here x was arbitrary, which I expressed in terms of delayed delta. Then I am trying to compute the response of the LTI system to arbitrary x. Bounded linearity, this can be pushed inside. I have to consider what is the response of the system to delayed delta. But the point is, system is a time invariant system. So k dot delta basically means that delta is passing through the delay system, which delays by k. This k dot delta can also be considered as Rk delta. So this is my notation that I am using, k dot delta to be delta function passed through a delay system. So I come back here, I rewrite this expression, and this can be written as xk r of Rk delta, basically composition of these two maps. First the delay system operates on delta, and then R operates on the resultant. But point is, our system is a time invariant system. So R commutes with the delay operator. So Rk is same thing as Rkr operating on delta. I can write this as xk because system is a time invariant system. I can swap the role of these two, but R delta as we have defined is nothing but h, right. So this can be written as summation, and this is nothing but h. Let me denote y as the response to x, and which we had written as xk Rk operating on h. If you remember my notation, this I would like to write as xk k dot h. K dot h is h delayed by amount k. So this is the map y. Now I want to evaluate this map y at an instant n. Basically that is nothing but I am evaluating each component of the map at instant n. That means I am evaluating k dot h at instant n, but this is nothing but the delayed version of h. So it is h delayed by an amount k, and this is a very important equation that we get in the context of LTI system. This sum is known as convolution sum, okay, and generally you write that y is equal to x convolved with h. This is just a notation that we use for convolution, x star h. One can immediately show by change of variable that convolution is a commutative operation. So I have some properties of convolution, that x star h is same thing as h star x. Convolution is commutative operation. Convolution also is an associative operation. So associative x, let me say x1 convolved with x2 convolved with x3 is same thing as, these equations are true for all x and h of our interest, and this is also true for all x1, x2, x3. So convolution is commutative, convolution is associative, and convolution distributes over addition. So that is the third beautiful property that convolution satisfies, that is x star h1 plus h2 is nothing but x star h1 plus. These properties are very vital properties when we try to analyze the system. They are quite handy. So let us see the implication of these properties in a particular context. All right. So what we have done so far, let me briefly summarize before I clear off the board, that you express any arbitrary signal x in terms of delayed delta function. Once we have that representation of any arbitrary signal x in terms of delayed delta function, we can immediately get a characterization of LTI systems, linear and time invariant systems. So this the characterization is actually nothing but a convolution sum. So if I know, please see one thing, if I know how the system responds to delta function, if I feed a delta function and I know what is the response of the system to delta function, that is knowledge of h is given to me, then given any x I can know what is the response of the system. I only have to convolve that x with this particular impulse response in order to get y, the output of the system. So h, that is the impulse response of the system, completely characterizes a linear time invariant system. Okay, the knowledge of h is sufficient to know all the details about LTI system. And also we saw that convolution is a commutative operation, convolution is a associative operation, and convolution is a distributive operation. Okay, let us see its application in simplifying certain block diagrams. Suppose I am having two systems, two linear time invariant systems, one output of one being fed to the input of the other. Such an arrangement is called cascading. I am cascading two LTI systems together. This is an LTI system, so it has to be completely characterized by its impulse response. That is, impulse response of this, suppose, is h1. This is another LTI system, so it is completely characterized by its impulse response. Let us say the impulse response of this is h2. Input to this is x and output is y. So I can immediately say this output is nothing but x convolved with, and let me say denote this output as x1, and this output I am denoting as y, or I could also denote this as x2, more appropriately as x2, right. Then I can say that x2 is nothing but x1, because input to this is x1 convolved with h2, but this is nothing but, if I write down from here the definition of x1, it is nothing but x convolved with h1, which is then passing through the other system h2. So it is clear from the associative property, okay, of convolution, I can write this as x star h1 convolved h2, which means I can, if I am having cascade of two LTI system, right, one has an impulse response h1, the other has impulse response h2, I can put the two impulse responses together, I can convolve two impulse responses, and I can produce just one system which will do the job of two systems, whose impulse response will be nothing but h1 convolved h2. So this means I can have one system whose input is x and the impulse response is h1 convolved h2 and output is y or x2, whichever you wish to call. Then I can also do the following thing. See, convolution also commutes, right. Now this is how this block diagram can be simplified and cascade can be put down into one system. Now how do we realize such systems? A very large class of discrete time LTI system is characterized by what are known as constant coefficient difference equation, constant coefficient difference equation, which I can write it in this fashion: y of n, or I am considering a system whose order is, say, m. In order to compute y of n or output at instant n, I am using past m value of the output. See, when k is equal to 1, I am considering y n minus 1, then yn minus 2, yn minus n. In order to compute the output at the instant n, I am using the past values of the output at instant n minus 1, n minus 2, n minus n. Similarly, I am using the present and past values of the input to produce an output, and I also impose a condition that the system is at initial rest. That means prior to the application of the input, the output is 0 and system is relaxed. There is input output both are 0 prior to n equal to 0, everything system is at rest. Under such circumstances, with this as the condition, the system can be treated as a linear time invariant system. Okay, then only it will be an LTI system. How do I realize such a thing? It's very easy to realize such a thing, because I require only 3 basic building blocks to realize such a system. One basic building block is unit delay, that is, I consider a delay d. So if x of n is the input, the output is x of n minus 1, delayed by 1 unit. When I say d, delay by 1 unit. Second basic building block that is required for the realization of such a system is nothing but coefficient multiplier. Coefficient multiplier. So if x of n is the input, and if I multiply with a coefficient say a, then output is a times x of n. Unit delay is one building block, coefficient multiplier, that is, some signal is coming, you multiply with a coefficient, you have to put down the arrows also to say where the signal is flowing, what is the signal flow diagram. And third is the adder. I am having, suppose, signal x1n, I can have another signal x2n, and I can have some signal say xpn, and output is nothing but sum of these, I going from 1 to p. It is an adder circuit. All these 3 basic operations can be very easily realized on a computer. I mean, you can have a small processor which can provide software delay. Multiplication is anyway a job of computer, and adder is also a job of computer. So the point is, whatever processing we do in the continuous domain actually can be done in the discrete domain. If we can find the realization of a system in the discrete domain, then entire operation can be realized in the software. And the beauty of this realization is that if you a delay remains a delay because it is a software delay, it is not going to change with time. Whatever you are multiplying with a coefficient, the coefficient is stored in the memory, that cannot change with time. And even adder will always perform the job of addition, no matter time or temperature, nothing affects that. So point is, these operations are not going to get affected by time because of aging and all that. On the other hand, if I have some operations like resistance, inductance or capacitance, they can vary with time. If they vary with time, you have designed the system to perform some operation, it may be performing some other operation after some time. But here, once you can have a computer implementation, okay, for whatever purpose you have designed, it will satisfy that all the time. So that is another advantage if I can realize a system in the discrete domain or in the, okay. So this is, again let me quickly rewind, this is a characterization, any linear time invariant system, if I am considering a linear time invariant system, constant coefficient difference equation with initial rest approximate a very large class of LTI system. Okay, so this is of main concern to us, constant coefficient difference equations. If I want to realize such a system, I require only 3 basic elements, a unit delay, a coefficient multiplier and adder. Using these 3 basic elements, I can realize any difference equation with constant coefficient, and which means if they are coming from an approximation of LTI system, I can approximate and realize that LTI system, right. Whatever we have done so far is time domain characterization of discrete time LTI system. So what I will do is the corresponding counterpart I will quickly write down for the continuous time case. Without going into too much of detail, we have to define a quantity called delta t. This cannot be called function because there are so many sequences which will behave like delta function, and delta function is given more by its property. So how do I define delta function? I say delta t is equal to 0 for all t not equal to 0, and in the vicinity of 0 its area is 1. That is, if I integrate this delta t dt, the area is 1 and entire area is concentrated in the neighborhood of 0. I can either write minus infinity to infinity, or I can write from 0 minus to 0 plus, one and the same thing, because the area is concentrated there. We consider, say, Gaussian density function. If I consider Gaussian density function, because it is a density function, the area is 1. Now I can play with the variance of that. If I make the variance very small, then what is happening is the entire area is getting concentrated around 0. In the limit, as the variance goes to 0, the Gaussian density function is going to behave as a delta function. Another sequence of signals which will behave as a delta function, let me say, is something like this. I am having a pulse whose this width is delta and whose height from here to here is 1 by delta as a function of t. So obviously area under this is 1, and if I make delta approach 0, then what will happen is it is going to shrink, but 1 by delta is going to go to infinity. But the area 1 by delta into delta will always remain 1. So the entire pulse is going to be concentrated around 0 with area equal to 1 constant satisfied all the time. So there are numerous sequences which will behave as a delta function. This is one characterization, one definition of delta function: delta t equal to 0, t not equal to 0, and area under that is 1. The another definition that I can give you, or another way I can define, is the following. Suppose I take delta t and ft is any other signal. I am assuming ft to be having a value defined at t equal to 0. This is nothing but f of 0. Integral delta t ft dt is f of 0. Immediately you can see one more thing. Suppose I consider the following thing. Instead of delta t, I consider delta t minus t0 ft dt. What will happen here? This delta function is non-zero only at t equal to t0, otherwise it is 0. So this is getting multiplied by a function. So 0, you are multiplying ft by 0 for all other values other than t0. So only at f t0 will survive, rest all will die. That f t0 can be pulled out, area under rest of this is 1. So this actually is nothing but f t0, and this is called shifting property of delta function. This is called Dirac delta function, okay, and this is a continuous time. This is in the continuous time context, continuous time counterpart of the delta function that we had defined earlier. So again, the important thing is any signal xt can be written as sum of delayed delta functions. That means I can write any xt as delta t minus tau d tau, and by following similar argument I can show that yt is nothing but x tau h t minus tau d tau, where ht is the impulse response of the system in the continuous time case. That is, ht is, or rather h is nothing but the response of the system to delta function, in the continuous time case. Okay, so this particular sum, which is this is ranging from minus infinity to infinity, is this integral is called convolution integral. So like the discrete time LTI system is characterized by convolution sum, the continuous time counterpart is characterized by convolution integral, and this convolution also is a commutative operation, is also an associative operation, also is a distributive operation. Okay, this satisfies all the properties. So whatever is applicable there is applicable in the continuous time case also. So this is the time domain characterization of LTI systems, discrete time and continuous time. Now let us define, and how did I approach this? I defined delta function, then I expressed arbitrary signal in terms of delta function, and I could immediately get a characterization. Now let us define another class of signals, okay, exponential signals, and then we will see that they also give rise to another characterization of LTI system, right? But before I talk about that, okay, let us observe certain things here. Because convolution is commutative, I could also write this as integral h tau x t minus tau d tau minus infinity to infinity. Because convolution is commutative, nothing changes. Now what I do is I feed an exponential type of signal here, that is, let me say that xt is e raised to power st, where s can be a complex quantity, sigma plus j omega, s can be a complex quantity. Suppose I feed a signal xt of this nature, okay, e raised to power st type, then what happens here? I can immediately see that response of the LTI system to an exponential input will be like this. Call it yt, doesn't matter. I am feeding an exponential input, this is what the response will be, from minus infinity to infinity. But this immediately I can see that it is nothing but e raised to power st, e raised to power minus s tau, h tau d tau, which is same as e raised to power st integral h tau, but this quantity depends on the impulse response h, and this also depends on what s I am taking. So this actually is nothing but, we can denote this as h of s e raised to power st. So response, what we have observed is response of an LTI system to an exponential input is an exponential input, and by expressing a signal in terms of only exponentials, we can find the response of an LTI system to arbitrary input, and that gives rise to frequency domain characterization of an LTI system. So what observations that we can make from here is that exponentials are actually eigenfunctions for the entire class of LTI systems. Alright, so if I am able to write, last remark let me make here, suppose I can write arbitrary signal xt in terms of skt, then the response of LTI system will be nothing but ak hsk e raised to power skt. So if I know how system responds to different exponential, I can immediately compute how it will respond to any arbitrary input. Okay, so that leads to another characterization of LTI system in terms of frequency, because these are exponentials are frequencies.